Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at some more antiderivative examples. In the previous video we talked about what an antiderivative was, and basically it is finding the function when you're given the derivative of the function. So if we're asked to find the antiderivative of f of x, we're going to find what we're going to refer to as capital F of x, understanding that the derivative of capital F of x is equal to small f of x. So given the small f of x, let's find capital F of x, or the antiderivative. When you have a polynomial function, it's fairly straightforward. You just take the antiderivative of each term by increasing your exponent of x by 1, so that would be x to the fifth, and dividing your coefficient by that new exponent of x. So that would be 3 divided by 5 times x to the fifth. And we can see that the derivative of this term is indeed 3x to the fourth. We do the same thing with the next term. So my power of x will be 1 plus 1, which is 2. My coefficient will be 7 divided by 2. And again, we can see that the derivative of 7 halves x squared is 7x. We could add a plus c to indicate that there could be a constant added to this expression, and the derivative would still be this. It gets a little trickier when we're working with power functions. Remember that when you do have y defined as a power of x, which we call u, raised to the power of n, the derivative of that will be n times that function of x to the n minus 1 times the derivative of that function u. So it's the derivative of whatever's in that bracket that's being raised to that power. So when we look at a function like this, we see that this is our u. So our u in this case is x cubed plus 4. Therefore, the du dx factor is 3x squared. And you can see that we have that there. So it needs to be in our derivative, but when we take the antiderivative, it's not there. It's a tough concept to understand. I want you to get an intuitive feeling for this. So when we're going backwards here, when we're finding the antiderivative, we start with our u, which is x cubed plus 4 to the power of, we add a 1, so that will be 6. We divide this coefficient by 6 to get a 1. And then, although that has to be there, it will not appear in our antiderivative. So is the derivative of this function this? Yes, it is. So it's a little tricky because you'll have you may have a function here that will not appear back in the antiderivative. Again, we can put plus c because we understand there could be a constant added to this function, and its derivative would still be this. Let's take a look at some more. As soon as you have something to an exponent, look inside the brackets and determine what the derivative of this function is. So the derivative of x plus 3 is just a 1. So we don't have to worry about that du dx factor. So when we find the antiderivative, it will be x plus 3 to the power of 1 half plus 1 is 3 halves. We take this coefficient and we divide by 3 halves. So 1 divided by 3 halves. Remember, when you're dividing by fractions, you multiply by the reciprocal. So that would be 2/3. And again, we can put plus c to represent a constant that we're unaware of. In our next example, we look at the function inside. It's 5x minus 2. The derivative of that is 5. We don't have a factor of 5. However, we can do a bit of manipulation when it's just the coefficient that we're missing. So what we could do is we could say, well, if I multiply by 5, that's okay as long as I also divide by 5. So this is still equivalent to this function. Now, this is like my du dx. It needs to be there, but I ignore it when I take the antiderivative. So my capital F of x, my antiderivative will be 5x minus 2 to the power of negative 3 plus 1 will be negative 2, and we divide this by negative 2. 1/5 divided by negative 2 will be negative 1/10, and we ignore that. We need it there, but now we can ignore it, and we can put our plus c. Let's check. Let's find the derivative of this. So if I were to find the derivative, it would be negative 1/10 times negative 2 times 5x minus 2 to the power of negative 2 minus 1 is negative 3 times the derivative of what's inside, and the derivative of what's inside is a 5. And if I take negative 1/10 times negative 2 times 5, that would give me my 1, so that would clean up to be simply 5x minus 2 to the negative 3, which is what I started with. So you can see that this is in fact the antiderivative of this function, because the derivative of this is that. Let's try some more. In the next example, I start by looking inside the power. I have a function 3x squared plus 1. So if we think of that as our u, the derivative of that is 6x. I don't have 6x, but I have an x, and that's the most important part. You can play around with coefficients, but you can't play around with functions, and x is a function. So I need a 6x. That's not a problem. I can simply multiply by 6 to get 6x, as long as I also divide by 6. So I haven't changed the value of the function, and this needs to be there in order to find the antiderivative, but it's not going to appear in my antiderivative. So now I can find the antiderivative, capital F of x, and I start with my power, so it will be 3x squared plus 1. I increase my exponent by 1, so to the power of 6. I take this coefficient and divide by my new exponent, so 1/6 divided by 6 will be 1/36. This would be the antiderivative. Let's do a quick check. Does the derivative of this equal this? So it will be 1/36 times 6 times 3x squared plus 1 to the power of 6 minus 1 times the derivative of what's inside, which is 6x. And when I clean all of this up, I will indeed get 3x squared plus 1 to the power of 5 times x, and the x can either be in front or behind. That's what I started with. It's important to look at what's inside the function, what's the derivative of that, and make sure you have that factor. If you have to manipulate a coefficient, that's fine. That's allowed as long as you balance it so that you don't change the value of your function. So if you have to multiply by 6, make sure you also divide by 6. In my next example, same idea, except in this case, the derivative of x squared minus 4 is 2x. I don't have 2x, but most importantly, I don't have an x. I need that x there. I can't make it up. You can't make it up and then divide by it. It's only the coefficients that you can play around with. So right now I can't find the antiderivative when it's in that form. However, I could expand this. So this function would be equal to x squared minus 4 times x squared minus 4. And that would be x to the 4th. I FOIL this. So it would be x to the 4th minus 4x squared minus 4x squared, which is minus 8x squared. Minus 4 times minus 4 is plus 16. Now that it's a polynomial function, I can find the antiderivative. So capital F of x will be equal to x to the 5th divided 1 divided by 5, so 1/5 x to the 5th, minus x to the power of 3. 8 divided by 3 is my coefficient, plus the antiderivative of 16 would be 16x, and again, I can indicate that there could be a constant added, and it would still give me this same derivative. So we can check, is the derivative of this equal to this? Yes, it is. So if you do not have the function part of the derivative of inside your power, you cannot find the antiderivative. If you don't have the coefficient, that's okay. You can play around with coefficients, but you can't play around with functions. Let's take a look at a couple more examples. In our next example, I want to write this as x squared minus 3x to the power of negative 4 times 2x minus 3. So if we take a look at x squared minus 3x, the derivative is 2x minus 3. So this is the du factor, which needs to be there, but it will not appear in the antiderivative. But I'm happy because that means I can find the antiderivative. So now I'm just going to take my u and raise it to the power of negative 4 plus 1, which is negative 3. I take this coefficient of 1 and divide by negative 3, so that will be negative 1/3. And then I can add a constant. This would be the antiderivative of this function, and let's just do a quick check by finding the derivative of this. When we clean this up, negative 1/3 times negative 3 is a 1. So it's this times this, which is this function. So it's very easy to check to see if you've done it correctly. Let's do one more example. If we take a look at this question, I always start by looking at what the function is inside the power. So it's 2x cubed plus 3x squared. The derivative of that will be 6x squared plus 6x. I don't have 6x squared plus 6x, but I do have an x squared plus x. If I were to multiply by 6, I would have the derivative of what's inside that power. So that's what I'm going to do. If I multiply by 6, I should also divide by 6. So I'll put the division by 6 in front. And then I'm going to multiply by 6, which you can expand if you want. But this whole thing is that du factor, or the derivative of what's inside the function. The derivative of this is this whole thing. It needs to be there. But when I take the antiderivative, I can ignore it. So the antiderivative will be my power, or my function, to the power of 4 plus 1, which is 5. Divide by 5. 1/6 divided by 5 is 1/30. That's my antiderivative, and I can quickly check to see if the derivative of this is actually this. 1/30 times 5 times 2x cubed plus 3x squared to the power of 4 times the derivative of what's inside, which would be 6x squared plus 6x. 1/30 times 5 is 1/6. When I multiply 1/6 through there, I will get exactly what I started with. You might notice that I haven't introduced any formal rules to do antiderivatives. I want you to have an intuitive understanding of the concept. If you have that understanding, you're going to find that when we move on to the next videos, we're basically doing exactly this. We'll practice, make sure you've got it, and then we'll see you on the next video.